Okay, now that we've talked about the first degree, the second degree, and now the third degree, we start kind of seeing a pattern where when you get to the nth term, nth degree polynomial, the nth term, uh, basically what's going to happen is if you did the derivative of that, you'd multiply by n the first time, then n minus 1, then n minus 2, all the way down to 1. And of course, that would cancel with n factorial, so that the nth derivative of this thing would just be the nth derivative of the original function at that point. So we kind of see that pattern coming out as we get to the third one. And so in general, we write it as the nth term as the nth derivative evaluated at that point divided by n factorial x minus a to the n. So we can write that in summation notation as the sum as k goes from 0 to n, understanding that the 0th derivative was the original function, taking that convention. Kth derivative of a over k factorial, x minus a to the k, of course, k is 0, x minus a to the 0 would be, of course, just 1. And remember that factorial is just that k times k minus 1 all the way down to 1. If our pivot point is 0, so if we take away the a and just make it x to the k, then this whole thing is called a Maclaurin polynomial. Maclaurin polynomial. So we're going to talk a little bit about some Taylor polynomials now for any size n we want. So first, let's say we want to construct the Maclaurin polynomial, so that's the pivot point of 0. For f of x equals sine of x, we want to do the fourth degree polynomial for that. So to do the fourth degree polynomial, we need to talk about the first four derivatives of sine. And then we're going to evaluate those points around x equals 0 because we're doing Maclaurin polynomial. So we're just going to go back to our polynomial. And so that would be f of 0 plus f prime of 0, x plus f double prime of 0 divided by 2 factorial, x squared, third degree, and then fourth degree, right? Writing out our terms as we go through here. So we will be doing P4 in this case. So we start by computing some of our derivatives for sine. And so we do f prime of x is cosine, f double prime, of course, would be negative sine, f triple prime then would be negative cosine, and the fourth derivative we would be back to sine because of that cyclical nature of the sine and cosine with their derivatives. And then we want to just take and evaluate all these values at 0. So f of 0, that would be going into our sine function. Sine of 0 is 0, so that's gone. Cosine of 0 is 1. Sine of 0 again is 0, so the second derivative would be 0. Third derivative, cosine of 0 would be 1, but with the negative sign would make it negative 1. And then for the fourth one, sine of 0 again would be 0. So P4 would be the first term, 0 plus 1 divided by 1 factorial times x minus 0 to the first power. Right. Plus the next term, the squared term, would be 0 divided by 2 factorial using our formula, x minus 0 squared, and then plus negative 1 divided by 3 factorial, x minus 0 to the third, and then the fourth term would be 0, so I'm just going to kind of just leave him off, right, plus 0, all right, plus 0. So I'm just going to leave. I kind of ran out of room, so I won't write the plus 0 because it's not going to really matter anyway. Just like that term's going to drop away, and that term's just going to drop away. So all we're going to end up having really for the fourth degree polynomial for sine, the Maclaurin polynomial, is just the x term and the cube term. So we have P4 is equal to x minus 1/6 of x cubed. X minus 1/6 of x cubed. So that's the Maclaurin polynomial, centered at 0. Okay? Or you could say Taylor polynomial, centered at 0. Maclaurin automatically is centered at 0. Okay? It's a special case of the Taylor polynomial. So let's say we want to do it for n equals 7. Well, we've already done the first 4 terms, or a 4th degree polynomial, so we just need to know the 5th derivative, 6th derivative, and 7th derivatives of sine, and what values they go to. So the 6th derivative at 0, well, derivative of sine would be right back to cosine again. 5th derivative would be back to cosine. Cosine of 0 is 1. When we go to the 6th derivative, we would do the derivative of that, which would take us back to negative sine, so which is going to give us 0 again for that coefficient. And then 7th derivative, we'd go from negative sine back to negative cosine. So we would be back to a -1 coefficient on this 7th degree polynomial. Okay? And so then, once we have this, let's go ahead now and plug this stuff in. So we already have the first terms up through 4, because the 4th term is 0. So the 5th term is going to be 1 divided by 5 factorial, x to the 5th, because it'll be x minus 0 to the 5th. The 6th term will just disappear. So the 6th term is just going to disappear. And then we would have the 7th term, which would be minus 1 divided by 7 factorial, which will be 50, 40, and then times x to the 7th. So there's our 7th degree approximation for sine. So the 7th degree polynomial that approximates the sine function. And the key characteristic is all 7 of its derivatives at 0 agree with the sine function. And the last thing I want to do is just show you what this looks like. Now, of course, this requires that our trig function be in radians. Right? Otherwise, these approximations don't work. Derivatives of trig functions, of course, are very different if they're not in radians. But there you can see the red graph there is the sine graph. That little blue graph there is my 7th degree polynomial. And you can see that on the graph, at least with my graphing device, it almost looks like it lays all over it pretty good, almost between 3 and -3. It's off a little bit once we get up around 3, but it's pretty darn accurate. And that's just a 7th degree polynomial. And believe it or not, this is actually what your calculators do when they're computing trig functions, is they have a certain level Taylor polynomial programmed into them that they use to compute trig functions. Probably has some other stuff programmed in with coterminal angles and things like that as well that allow them to be accurate for really big angles. But they have some polynomial programmed into them of some sufficiently big enough degree that they then use to compute your trig functions to a fairly good level of accuracy. Okay, and so you can see this is pretty good for a 7th degree polynomial. Fairly accurate, at least looking in here. Now we could zoom in real far in this graph and see that probably the only place it's exactly the same is at that one point, but it may overlap at a few other points, I don't know. But it does at least lie fairly close, at least for quite a while there. So it's a pretty decent approximation.